Hello everybody. In this video I want to discuss one very important point regarding the degrees of freedom analysis using the two methods that we discussed, the atomic balance and the extent of reaction methods. And the reason I'm discussing this point here is that there are some problems that the degrees of freedom analysis for reactive systems using the atomic balance method is misleading. And it produces, I wouldn't say wrong results, but misleading results. And just to clarify this, let's take this example of ethylene oxide production by the oxidation of ethylene. So ethylene reacts with oxygen to produce ethylene oxide, and I will take a very simple case where we have ethylene, 100 moles of ethylene and oxygen fed to the reactor, and we don't know how much oxygen is there, but what we know is that the ethylene is totally consumed, so we have no ethylene in the product stream, and we have in the product only ethylene oxide and oxygen. So I don't want to go through the solution or find the flow rates or the missing flow rates or anything. I'm interested in the degrees of freedom analysis now. So if we want to perform the degrees of freedom analysis, we have two options. So we are going to do this using the two methods that we covered, the extent of reaction method and the atomic balance method. So for the atomic balance method, we calculated the same way we do every time. We have number of variables minus number of given variables minus number of equations minus number of additional relations. So if you look at the problem that we have here, the number of variables, again, this is the atomic balance method. We have 1, 2, 3, 4 variables. We have only one given variable. We have 3 equations, carbon, hydrogen, and oxygen, and no additional relations. So the degrees of freedom is going to be 0, which means that the problem is solvable. Okay. Solvable means I can calculate all the unknown variables using the information that we have right now and the balance equations. So I don't need any extra information to solve the problem. So let's see if we do this using the extent of reaction method. So for the extent of reaction method, we are going to use the same equation. The number of variables here is going to be 1, 2, 3, 4 plus the extent of reaction. So we have 5 variables. We have one given variable. We have 3 balance equation, ethylene oxide, and oxygen, and no additional relations. So the degrees of freedom is 1, which means that the system is not solvable. So I need one extra information to calculate the missing variables. So now we have a question that we want to answer. Which one of them is right? Is it is this system solvable with the given information or not solvable? Because we don't know. Or does it mean that I can solve this system using the atomic balance method and I cannot solve it using the extent of reaction method? This is also one question that, or one interpretation of the results. But this is, according to what we said before, both should be the same. The degrees of freedom using both methods should be the same, and this is what we saw all the times before. And we have to agree that the system would be either solvable or not solvable with the given information. So it's not possible that we can solve the system using the atomic balance method and we cannot solve it using the extent of reaction method. So there is something that we need to clarify here. And to clarify this, we need to look closely into the balance equations of the reactor, the mass balance or the material balance equations using the atomic balance method. So if we apply the balance or write the balance equation on carbon, so it's very simple and straightforward equation. It's 100 times 2 equals the number of moles of ethylene oxide times 2. So it's very simple, very straightforward. We can use it directly to calculate the number of moles of ethylene oxide in the product stream. Now if we write the balance equation on hydrogen, it's going to be 4 times 100 equals 4 times the number of mole of ethylene oxide in the product stream. Now we would see that there is some interesting thing that we see here. What we see here is that these two equations are not actually two independent equations. This is only one independent equation and the other is dependent. This equation is the same as this equation but multiplied by 2. So these two equations are actually only one independent equation. The second one is dependent. So actually, in the equations that we have now that we should include in the degrees of freedom analysis is 2, not 3. So we have carbon and oxygen, or hydrogen and oxygen. Carbon and hydrogen are the same equation. Okay, so if we put the equations, a number of equations is 2, then we will have degrees of freedom 1, which means that we are getting the same result that we get in the extent of reaction method. So the right answer is 1, not 2. Of course, this thing might be confusing. Okay, so this is what we used to do from the beginning of doing the degrees of freedom analysis for reactive systems using the atomic balance method, and we used to do this all the time, and we never saw this problem. So this is something that is repeated in many cases, and this is something that you can predict from the beginning. So the carbon started as two atoms in the ethylene molecule, and it ended up to be 2 atoms in the ethylene oxide molecule. The same in the same reactor, hydrogen, which was accompanying the hydrogen as 4 atoms, the carbon as 4 atoms, it's now accompanying the carbon as also 4 atoms. So the equations must be the same. So it's something that you should expect from the beginning. I know that this is something that you might not notice from the beginning, but this is just giving you a hint that this is something that might happen. So I don't want you to go through the solution and take the atomic balance degrees of freedom for granted, and now the system is solvable. And now if you look at the equations, you'll not be able to do the balance or calculate the number of moles of oxygen in the feed or in the product. If you write the balance equation in oxygen, it will have one unknown variable here and another unknown variable. It's one equation and 2 unknowns, so you cannot solve it. Okay, so this means that you need one extra information, and it means that the degrees of freedom is 1. So this is a very clear thing now. You can see it clearly after going through the equations. So this is what I want to highlight here. Let's take another example here for ethanol production using the reaction of ethylene with water. And this is the first reaction. The second reaction, we have ethanol reacting, 2 molecules of ethanol reacting to produce diethyl ether and water. And we know the feed to the reactor, which is ethylene, water, and inerts. We don't know any flow rates, we don't know any compositions, and we know the product flow rates, or the flow rates of all the components in the product stream. And I don't want to solve the problem, I just want to perform the degrees of freedom analysis. So if we do the degrees of freedom analysis using the 2 methods, we would see also similar thing. If you do it using the atomic balance method, we have 1, 2, 3, 4, 5, 6, 7, 8 variables. We know 5 variables, and we have carbon, hydrogen, oxygen, inerts. So we have 4 balance equations, no additional relations. So degrees of freedom is -1, which means that we have one extra information. So if I get rid of one of these information, I can solve the system because it's an extra information. However, if we do the degrees of freedom using the extent of reaction method, the number of variables we have is 1, 2, 3, 4, 5, 6, 7, 8 plus 2, which are 2 extents of reaction. The number of given variables is 5, so we have 10 variables. We know 5 of them. We have 5 balance equations: ethylene, ethanol, diethyl ether, inerts, and water, and we have no additional relation, so the degrees of freedom is 0. So now we have the same thing, the same case. We have 2 different degrees of freedoms, or values of degrees of freedom using the 2 methods. So again, to clarify what we have and to find out which is the correct one, let's look at the equations of the atomic balance, the mass balance, the balance equations using the atomic balance. So if you do the balance on carbon, we have 2 times the ethylene in the feed equals 2 times 43.3 plus 2 times 2.5 plus 4 times 0.14. So this is a very simple equation, straightforward. You can calculate the number of moles of ethylene in the feed stream. If you do the balance on oxygen, we have the number of moles of water times 1 in the feed equals 1 times 2.5 plus 1 times 0.14 plus 1 times 44.76, which we can directly substitute in this equation to calculate the number of moles of water. Now, again, let's go to the degrees of freedom. We said we have 4 equations: carbon, hydrogen, oxygen, and inerts. So we use the carbon and oxygen, and the inert equation is going to be very straightforward. I can get it by just looking at the numbers. It's going to be 9.3 moles. So the in equals out. It's not part of the reaction. So it's 9.3 moles of inerts in the feed. So I used 3 equations only: the inerts, water, and the ethylene, and I calculated everything. There is nothing missing. I have no unknown variables that I will use the last equation to calculate. So if I write the last balance equation, which is the balance on hydrogen, it's going to be 4 times the ethylene in the feed plus 2 times the water in the feed, which I already calculated from the first 2 equations, equals 4 times 43.3 plus 6 times 2.5 plus 10 times 0.14 plus 2 times 44.76. And if you substitute, you'll find that the left-hand side equals the right-hand side, so it's not adding any new information. Okay, so this equation is not adding anything to me. And if you look at the equations closely, you will find that if you multiply equation 1 by 2 and the equation 2 by 2 and add them together, you're going to get this equation. So let's see. 2 times the C2H4 in stream 1 is this. This times 2 is this. 43.3 times 2 is this. 2.5, it's already there and there, so it's 2.5 times 5. If you add these two together, then multiply them by 2, it's 3. 2 plus 1 is 3, times 2 is 6. 0.14 is 4 plus 1 is 5, times 2 is 10, and 44.76 times 1 times 2 is this. So it's 2 times equation 1 plus equation 2 is going to give us equation number 3. So again, we're getting the same result. So the equations that we have now are not 4 independent balance equations. We have 3 independent balance equations. So if we go back to the degrees of freedom, this should be 3 and this should be 0, and we will get the same thing. So the take-home message of this is that you have to be careful when you do the degrees of freedom analysis or calculate the degrees of freedom of a reactive system using the atomic balance method. In many cases it will work and it's going to be fine, but in some cases it will be misleading. So my suggestion is either to do the degrees of freedom using the extent of reaction method, even if you are going to solve using the atomic balance method, it's fine. But just to make sure that the degrees of freedom is done using a method that will not produce misleading results. Or if you do the degrees of freedom using the atomic balance method, you can double check with the extent of reaction method. It's not going to take a lot of time. It's just this number and this number that is different. Otherwise, everything is the same. So you just add the number of reactions and calculate the number of variables using the extent of reaction method. This is not going to take more than half a minute or 1 minute maximum. But by doing this, you are making sure that what you get is correct and it's not producing wrong results of the degrees of freedom. And then when you go to the solution, you will find out that there is one equation that is not helpful. It's not adding anything. So I hope this is helpful, and goodbye.